Our next speaker is Michael Ferreira, and I do want to make a note. There was an incorrect email address that may be in your literature that you received, probably in a large book. And if you just refer to the email address that was listed at the top of his paper, that is the correct address. But please welcome Michael Ferreira. He is a Senior Fire Protection Engineer and Project Manager with Hughes Associates.
Good afternoon. It's a pleasure to be here speaking at the 8th World Congress. My presentation actually follows quite nicely behind Martin's. I'm going to be talking about a very specific issue, protection of the stair enclosure in high-rise buildings, which obviously is very important because until we get widespread use of elevator evacuation, stairs are the primary means for protecting people and getting them out of building in an emergency event. Before we leave the title slide, I wanted to tell you that the building shown is representative of what Martin called a normal high-rise building, 30-story tall building, that are present in quite large amounts in the United States, the 10 to 50-story variety. It's the Four Seasons Hotel and Residences in downtown San Francisco. It's a very significant building for me because in 1995 it was the first building where I was responsible as the engineer of record for the design of the smoke control and stair pressurization systems. It's also pertinent to this talk because it's a building where I almost lost my hand when the stair door slammed on me while commissioning the building, and we hadn't balanced the stair pressurization systems properly yet. So it is pertinent to this talk. My objectives in this talk are first to show a real-world example of how the performance-based fire protection engineering analysis can be beneficial in solving problems for the design of tall buildings. I've long thought that the fire protection community lagged some of the other design communities, such as architects and structural engineers, in the use of performance-based computer modeling and unique design elements in the design of buildings. For too long, we were mired in the approach of looking in our code book and seeing how we could wrap this very prescriptive requirement around, in some cases, a very unique building. Second, I want to discuss the environment within the stair enclosure as a result of a fire-rated event in a high-rise building. And finally, to discuss whether it's time to examine new protection schemes for stairways, given what I think are new design considerations, such as full building evacuation, what can happen if there's partial stair damage or other direct communication of smoke into the stair, or special events like terrorist events, chemical, biological agents that are involved simultaneously to a fire. In the U.S., there are several different levels of design standards, from the building code, the most commonly used one, the International Building Code, which defines stairs as being smoke-proof enclosures. There are three alternatives recognized, but by far the most commonly used alternative is stair pressurization. Natural ventilation requires an exterior balcony. Mechanical ventilation requires the use of a vestibule, and architects don't want to give up the space to do this. The NFPA also provides their own requirements with regard to pressurization systems, and in many cases there are unique local requirements, such as the New York City Building Code, which has its own unique twist on stair pressurization. Very simply, a stair pressurization system, it's putting a fan most often at the top of the building and injecting air into the stair in many different levels to pressurize the stair. Single injection is possible if you have smaller stairs. It creates a balanced pressure and keeps smoke out of the stair. And the logic in the code is that it creates a smoke-proof enclosure, but I would argue, does this really create a safe haven from smoke in all cases? The basic assumptions, stair pressurization rationale developed over 20 years ago based on a limited amount of testing. A very simple approach, and with all stair doors closed, the argument is if you put enough air into the stair, you can keep smoke from intruding into the stair. The design assumed that all doors would primarily remain closed, that a limited number of people would access the stair, and then the stair would then become a closed environment again, and the pressurization system would keep smoke out. And usually the approach that's been used through time is to evacuate the fire floor, the floor above and floor below. And the advantage of this system is performance is readily measurable. Once you build this thing, you can take your pressure gauge out into the field and verify that you do in fact have the pressure differentials that you need. Minimum pressure differentials, they're based on the temperature and the buoyancy force that can be created in a fire. And the curves show that you have less buoyancy force, less temperature in sprinklered fires than non-sprinklered fires. And as a direct result of the pressure that can be created, that's the design pressure in the code. The maximum pressure has been developed based on a maximum door opening force. How much force can somebody exert and be reasonably expected to open up the door to access the stair in the event of a fire? And there's typically a tight range on that. And the one thing I would like to point out is there are a lot of disconnects in the code. There are certain sections of the code that allow pressures up to 90 pascals, for example. But then there are, in the United States anyway, there's the Americans with Disability Act that requires less than half that in some cases for doors to make sure that all people can access the door, including the disabled. And there's lots of arguments and interpretation with local code officials over when is that applicable. In a fire exiting event, can you assume that they will be helped to access the door? But there are some performance issues that I've identified over time in my experience with this in dealing with stair pressurization systems. First of all, they may not be able to maintain the proper pressure differential under all stack effect conditions, and I'll demonstrate that it doesn't take much of a stack effect to really foil this approach. Overpressure conditions can be made worse in combination with a smoke control system. In other words, there are certain codes that require that you exhaust the residential corridor, for example, and you get a push-pull effect on that door, which can really exacerbate the overpressure conditions. And finally, you may not be able to maintain the pressure differential whenever you have open doors or partial stair damage, such as in a terrorist event. And finally, if you do have any of these failures and you have an introduction of any kind of agent that you don't want into the stair, whether it be just the smoke itself or also some other hazardous agent, this pressurization system can then help distribute that to other floors. One question I'd like to ask is the assumption of staged evacuation still valid? And I highlight the 1993 World Trade Center bombing instead of the 9/11 events, because the 9/11 events, I think we can all agree, were fairly extreme. There was a large extent of damage to the stairs, very large, very extreme fire event. I focus more on the more realistic 1993 bombing, where there was a localized damage to the building that, due to the intense stack effect on that day, it was very cold, had smoke inundating the stairs, there was loss of power, and basically blackout conditions. People were exiting using the stair and they couldn't see a meter in front of their face. And because of these events, and especially the psychology of 9/11, will people stay put when they're told to stay put, when they hear the alarm? Well, there's something going on in the building, but on your floor you're safe, so please stay where you are. I would argue that after 9/11, there's going to be a certain subset of people that will attempt to evacuate the building, and this could cause some major concerns with regard to your assumptions regarding the use of the stair. Stack effect has been talked about quite a lot, issues in designing super tall buildings, but I will say that there's a normal stack effect, which I'll be addressing in my analysis because I was really focusing on a lot of buildings in the United States, but a reverse stack effect is, in a hot climate, is very evident here in Dubai, but the conclusions and behaviors are roughly the same. We can readily model stack effect flows, look at the air patterns and how these patterns develop within the stair. And for the purposes of my example, I modeled a winter stack effect, given an ambient temperature of -4 degrees C. And I did a 30-story building for the purposes of the analysis. I used the Contam building airflow model and an existing Contam model that I had for a building that I just happened to be evaluating for an industry group, the impact of elevator lobbies on vertical smoke spread. But we use this model to look at how big does the building have to be before the stair pressurization is compromised. Now what this table shows, I looked at two different design temperatures, and there's two different design temperatures readily used in the United States, one provided by ASHRAE, the other provided by our National Oceanographic and Atmospheric Administration. If you look at the number of stories and the various design temperatures, there are a couple of things that you can pull out of this table. From the first line over on the right in blue, all you have to do is open one door to your stair and hold it open, and you've basically reduced the pressure in the stair less than that is required to hold back smoke. Then as you carry this forward and you increase the height of the stair, you make the temperature extreme worse. In the event of even 20-story buildings, it does not take much of a combination of open doors and temperature to make sure that you can't pressurize the stair to the extent that you need to keep smoke out. And you look at this, and it's only 25 and 30-story buildings where you're having this problem. You can imagine this problem to the extent of the super high-rise buildings. There are lots of things that you can do to minimize stack effect, intermediate doors, modulating systems. An analysis that was done in this month's CTBUH journal says that the stack effect for the Burj Dubai is 320 pascals. Very extensive, much higher than what I'm talking about. The unfortunate thing is that intermediate doors and transfer corridors are not desirable to architects. I'm talking mainly in a classification of buildings from 10 to 50 stories where architects in the US anyway are very hesitant to put in elevator lobbies. They'd rather pressurize the elevator shafts and pressurize the stairs. And stairs tend to be remote from the elevators, not in one central core that can be protected, such as the Burj Dubai lobby that is exhausted with a flow through of air. And the stairs tend to sit remotely by themselves and have to be protected on their own. Final thing is that modulating systems are very difficult to design properly. Modulating systems, they typically utilize a number of different components: barometric relief dampers at the top of the stair, variable speed drive fans controlling the stair fans, and pressure sensors at multiple locations within the stair to look at, what are the maximum pressure conditions. These systems are slow to react to the opening and closing of doors that change conditions quite rapidly, and definitely have the potential to overpressurize stairs. I'll give you a brief example. We had a small 20-story building that we were testing in Minneapolis, Minnesota, which was a jurisdiction that's very cold in the United States, quite prone to stack effect. They had a system, when we came in to do the testing, the system was already designed by the mechanical engineer, and on paper it looked like it had been well thought out. They had pressure sensors, high, low, and medium elevations in the stair, programmed to say when is this pressure less than the minimum required by code, and then ramp up the fans. They also wanted to include plenty of safety factors, so they took the design pressurization number and multiplied that by 2, so they had double the fan capacity. And what we found, and we actually found this in quite an interesting way, I was on the phone with my test engineer who was standing there holding the door open. We were talking about different tests that we needed to run. And then he stepped out of the way, and unbeknownst to him, the fan on the roof had ramped up to its maximum capacity. It slammed the door. It sounded like a gun going off. Luckily, he wasn't standing in the stair. We had to take a hard look at the design, and what we did is we put in programming logic that no matter what, even under these worst case conditions, you wouldn't allow the fan to go over a maximum speed so that you wouldn't allow this overpressure condition. And you can imagine if this happened and the fan ramped up, one, you have the hazard of the door closing on occupants in a very rapid fashion, but you also have a period of time when the door closes where the door pressures exceed that which it takes people to get into the stairwell. If you have excessive overpressures for too long of a time, you can imagine a very minor fire event where people would normally be able to use the stairs and get out of your building that could potentially harm someone because the stair pressurization system didn't allow them to get into the stair. Commissioning issues, very briefly. The main issue with commissioning is that people will often test the building in a very mild temperature condition and be right on the range of that allowable pressure differential and not test it in the dead of winter. Not go back and test it because the building was signed off on and they won't test it under maximum conditions. So now you have a building out there with an unknown maximum condition that could create a very real safety hazard. So I'd like to propose a new protection scheme. It's something I've thought about for a while. And again, it takes advantage of this performance-based evaluation. Looks at tenability analysis in the stair, use of new tools such as Fire Dynamics Simulator. Tenability analysis actually has developing a pedigree within the fire protection community and more of an acceptance by approving authorities. And what we did is we used both a high throughput supply and exhaust to ventilate the stair and basically purge the stair. It's a neutral system. No net pressure differential on the stair, doesn't impact by itself door opening forces. Modulating systems are not needed in moderate high rises. It simplifies it. And the exhaust itself can be used as part of a more programmed sequence to alleviate stack effects. It can be used, it isn't just sitting out there as an unused system. In a normal everyday condition, it can be used to alleviate stack effect forces and may prevent or may allow longer stair runs in super tall buildings. So what I wanted to do is a very brief, this was not based on a real project, it's all a hypothetical exercise. I looked at 3 different schemes. One is doing nothing under a couple of different stack effect conditions. The second is pressurizing your stair, a very simple system that meets the code. And the third system just basically matches that amount of supply you put in for pressurization with an equal and opposite amount of exhaust, not optimized in any fashion. Use fire dynamics simulator, 15-minute run times, and the one thing, -4 degree stack effect. And again, you've seen this a couple times today, but I use as the criterion for evaluation visibility distance. We also can look at tenability and temperature as well. And you've seen the 10-meter criteria, which is kind of developing, again, a pedigree within the fire protection community as being potentially dangerous to life. So what you see on the left is the baseline. This is an unsprinklered fire with the door closed. It's a very hot fire, or it's a fire that's shielded from the sprinklers, that the sprinklers aren't very effective, so again, you're building up hot temperatures. And smoke is escaping through the leakage in the door. Now, we assumed a leaky door, because of course, if the door was hermetically sealed, no smoke would get out. But it's a fairly leaky door within the allowable range. Now, in the middle, you can see that if you're pressurizing it and nothing else is happening, no smoke gets into the stair. But if you do the dilution, you're also exhausting the smoke at such a rate where you really aren't building up any smoke levels of concern in the stair. This is kind of the maximum achieved. It's very localized. Their visibility distance for only a couple of floors of the stair, which are very passable. It's a very good system. Case 2, what we wanted to do is exacerbate the stack effect, and what I think this corresponds to is the full building evacuation, where people are all trying to use a stair, and in some way, shape, or form, doors are being held open throughout the stair because people are trying to access the stair, there's a queue, and they can't get into the stair. And we basically held all the doors partially open, but you could assume that some doors were all open in various combinations. Now, what this shows is based on versus doing nothing, which puts quite a lot of smoke into the stair, it looks fairly equivalent between the pressurization and the dilution system, but it's misleading because the stair pressurization achieves this improvement over the baseline by pushing the smoke onto other floors. There's no smoke removal from your building. It's all staying within the building. So you're basically inundating some other floors with smoke. The dilution system, we found there's very little smoke intrusion into the other floors because, again, you're only holding the door open somewhat. The stack effect is exacerbated, and all of this, the improvement you see there is because smoke has left the building. You're removing it from the building. The final case is this catastrophic case where what we did for the sake of the model is we just left the door to the fire compartment open, but it can be any kind of damage or anything where the stair door has been compromised, and again, you have a wide open stairwell. Now, all 3 cases are not optimal, as you can see, but again, what you're doing is you're probably, and again, we haven't optimized this, just a 50% increase in this flow-through rate could really improve the situation on your right. But you have reduced it somewhat, and you have reduced it to the point where people can at least see to negotiate the stairway and they're not in a blackout condition. And again, looking at the 2 cases on the right, any smoke that's left that stair is being pushed into the rest of the building with the pressurization system, and the dilution system is being removed. I don't have the real-time model, but we did look at sprinkler cases, and the one thing I can tell you is that if everything works properly, you probably don't need stair pressurization to begin with. You have your fire barriers, you have doors on door closers, they're gasketed, you have the sprinkler system controlling or putting out the fire, and in this case it's only controlling it, it's not extinguishing it, but it's keeping it to a much lower fire size. And I left the door open, and both systems, again, keep the stair fairly clear. The dilution system removes most of the smoke. The pressurization system pushes it around. And when you have the door closed, there's nothing in the stair. If everything works properly, you don't really need anything with regard to the stairs. Okay. The conclusions of our modeling is that I believe that this high throughput stair ventilation system can be a really effective alternative for protecting exit stairs in high-rise buildings. Provides fresh air to building occupants, removes and dilutes the hazardous gases, and the design isn't as sensitive to stack effect. In fact, it's not sensitive to stack effect. The effectiveness of the system has not been optimized. I took this on as purely an academic exercise, but I think if you optimized it based on flow rate, if you have to pay for the fans, you have to pay for the shafts and all that, you can probably get away with even more of an increase in the flow-through rate and get a lot better performance. And we have now verified the effectiveness of the approach for stairs up to 50 stories, reverse stack effect. I mean, it's easier to look at buildings in this aspect ratio I've shown, the 20-story range, versus a long, thin building. You can analyze the results better, but all of the conclusions I've shown hold. One quick slide I like to show is that degree of visibility and improving the visibility in the stair can be enhanced by doing something like exit path marking, so that you have that increased awareness of the stair treads and how to get out of the building, and that can even make this dilution system that much better. So in summary, I believe that stair pressurization systems must be properly designed to avoid adverse conditions. And I truly believe, based on what I've seen and just anecdotal evidence, that there are stair systems that were designed right on paper, were tested under optimum conditions, but really could be unsafe, and they exist in buildings today. And we won't know until there's some minor fire event and people can't get out of the building and there's some sort of injury. Better alternatives may exist, and the performance-based approach allows us to evaluate these, and it's come time that we do look at alternatives to stair pressurization. There's fewer failure modes to this approach. Currently looking for a real building to apply this approach to, so if you've got one and you're interested in talking to me about it, I'll be sitting right over here. But I really am anxious to apply this and really take the modeling to the next level and to put it into a real building and take it all the way through approval by a code official. Thank you very much.